So from the last video, we determined that this was our equation, or sorry, this was our graph for a pendulum or any other simple harmonic motion. And now I'm introducing you to the equation for the pendulum that would explain this graph. And if you look at it, we know that the graph is cosine dependent on t, so that's why we have t here and cosine there. We know that when cosine theta, whatever is in here, whatever is in the parentheses, whenever this equals 1, this equals the cosine, whenever the parentheses equals 0, whatever's in here, whenever this is equal to 0, it equals cosine equals 1, which means that A would have to be the value whenever inside equals 0, 2 pi, 4 pi, so on and so forth. So for whatever multiple of 2 pi, we get cosine equals 1. Therefore, A has to be the maximum value when cosine theta equals 1. We made this 2 pi and not 4 pi or 0 pi because if it was 0, it would just cancel out anything in here and it would always be equal to 1, and that's not the case. And we included the t on the bottom, the period on the bottom, so it can cancel out with t. And we will, as we'll learn later, that the position depends on the period. So it also makes sense that when t equals 0, x equals the amplitude. So when these two are equal at this point, that equals 1, which makes this 2 pi inside here because those cancel. And when this is 2 pi, cosine is 1, so A is equal to x. Okay? Now, if you're still not buying this, just make sure that these 5 points, you can pause this video after I write down the 5 points and just work it out on your own just to make sure that you believe me. So at point 1 here, that's at the start, x equals A when t equals 0. Okay, so just pause it after I'm done to work that out. At point 2, it passes through, the pendulum passes through x equals 0 at t equals 1/4 the period. At point 3, x is equal to negative A at t equals 1/2 the period. At point 4, x again is equal to 0, passes through at t equals 3/4 of t. And lastly, at point number 5, when it starts to repeat, x is equal to A at t equals t. So you can go through pause this, work it out, make sure that at each of these t's, these are the values that you get when you plug in t at those points. Make sure that you are satisfied that this equation works. Okay, so if you've done that, if you've paused the video, moving on, we also said in the last video that frequency is equal to 1/t. So, or 1 over the period, which I can then sub in to this equation, and I can have x of t equals A cosine 2 pi t frequency. So if I have the frequency instead of the period, I don't have to do an extra equation. Now we also know from chapter 7 that omega is equal to 2 pi over t. This is the angular velocity in chapter 7. In this chapter, we're going to call it the angular frequency. And we can sub this right here into our original equation, and we get something even easier. X of t equals a cosine omega t. Now, if we take the derivative of position, we get velocity. So derivative of x dt equals velocity. So if I take the derivative of a cosine, you have to know that dt, I'm just setting up a general equation right now. So if I do this, this is going to equal negative AB sine bt plus c. I can also do this for sine bt plus c equals AB cosine bt plus c. So these are general forms that you have to know for sines and cosines. If you take the derivative of the sine, you get a cosine. If you get the derivative of cosine, you get negative sine. So if we take the derivative of our x equation, using this right here, we get b of t is equal to negative omega a sine omega t. And if sine equals 1, then negative a will, then negative omega a will equal negative b. And since sine can't be any greater than 1 or negative 1, we can say then that this is actually our maximum v. And then lastly, if you take the derivative of velocity, again, we use the same set of equations here. I get negative omega squared a cosine omega t. And there I have all my kinematic equations for simple harmonic motion. Okay, that covers this video. And in the next video, we'll cover circular motion. Bye.